Welcome to the third part of our Biosphere lectures, and this is still Geology 6351, Mapping and Cartography. So this is 3 parts of a 4-part series. We've been talking about cycles, and we're going to continue on with consideration of the water cycle. We've already looked at how atmosphere influences carbon and the movement of carbon and nutrients, and this diagram is showing us a lot of parts of the water cycle, but we'll start with the atmosphere. And there is water storage in the atmosphere. It comes from sublimation of ice and snow, and it also comes from evaporation from the oceans and evapotranspiration from plants. And so the water cycle is definitely continuous. You can start really anywhere in the process, and we're just starting with how does the water content get into our atmospheres. And so evapotranspiration is where plants are processing sunlight energy and carbon dioxide and water to make sugars, and they also produce water. And oxygen. And so a great deal of the oxygen in the environment comes from this evapotranspiration. If you think of large forest stands, they're accessing water in the water table or underground water that isn't on the surface and is not available for evaporation. And it's a great contribution to the water in our atmosphere. Of course, we have condensation that comes from water, and this comes from fresh water and primarily water in the oceans, because the oceans cover a greater portion of the earth than our freshwater areas do. We continue on with the water cycle after water is falling on the earth or is deposited in the form of water storage in ice and snow. It will stay for a certain amount of time. In some areas, it continues to exist, such as a glacier, but we also get melting of that snow, and the runoff will go to streams. We also have forms of precipitation as rain, and this is part of the visible water cycle on the surface. It does sink into our groundwater and below ground storage, but there is also stream flow and storage areas like lakes and ponds. There is a great deal of surface runoff that does indeed go to the oceans, and the water will contribute or dump right back down into our oceans and be subject to evaporation. There's a significant part of water that, through the process of infiltration, becomes groundwater storage. And if you've ever been in a place where you needed to access this type of water, you would get it usually from a well or an aquifer. And groundwater makes up a great portion of the available fresh water on Earth. And this is the water that most of our larger forests access, and people are beginning to access it as a form of water more and more. So there's many different ways that humans interact with the water cycle, which is not surprising. Water is essential for life. You may have heard the rule of threes, that if you are in a stranded or emergency situation, you can go 3 minutes without oxygen, 3 days without water, and 3 weeks without food. So that's just a general consideration. Of course, there's a lot of variables, but it shows you that water is pretty important to a human body. And there's other ways that humans will use water. So the the main message here is the rate of our water extraction from rivers and aquifers rises with increasing population. We use water for irrigation, for crops. We use water in industrial uses. It's used for hydraulic fracturing, and These over here, groundwater recharge and surface water recharge, are processes that humans will use water for in order to continue, for instance, agricultural piping of water, and groundwater recharge also for the growth of crops is human use, and then municipal use. And so um, the the applications of all of the people living in urban and municipal areas. So if we look at global usage of water in a spatial perspective, this is data from 2010, but it's really great side-by-side data. So it gives you a good sense for where the concentration of water usage is happening around the world. And so we can see that in the United States, we have a high focus or emphasis on irrigation, and the legend is not showing here. I apologize for that. I'm not sure if it's in the article that I got this image from, but I do know, because I know that the blues are higher values than the yellows or the greens. So intermediate would be green, high is blue, and low is yellow. So I apologize that there's no color bar in there, and I hope you noticed, because I hope you're starting to really think about maps as messages or tools for messages, and that you could really benefit from having a color bar here. So I'm going to keep that in mind for the future. But let's just carry on. We know now that the blues are the highest areas. And so if we look at the highest areas of irrigation, this is the part of the United States that is mostly cropland and farm area, what you might call the middle or central US. And then we look at parts of Asia where there's a lot of water used for irrigation. You'll notice there's not very much irrigation use in Africa. So most of their farming is done in areas where irrigation as a technology isn't needed. If we think about domestic use, so domestic use is concentrated in the US on the eastern seaboard. We have concentrations in Asia, and we have a high concentration of domestic water usage in Europe. Now, again, not so much in most of Africa. For domestic uses, they are often pretty agro-rural, or they are using water in ways that's very sustainable. Electricity generation, again, we see a pattern where it's focused here on the East Coast in the United States and in Europe, if we consider Africa, Asia, and Europe. And I haven't really been mentioning much about Australia. One thing that you might notice in these maps, if you look at the continent of Australia, is that the data is mostly concentrated on the eastern and especially the southern eastern portions of Australia. Much of the interior is relatively uninhabitable. There are some Aboriginal tribes that live in the outback, very, very, very few. So the population is very, very small, especially compared to most of the rest of the world. The same is true of much of South America as well, and parts of Africa. Not a lot of population there. Okay. If we look at water for mining, we see a pattern. Again, we have a concentration near the Great Lakes in the United States. And then finally, in manufacturing, it's interesting to note that not only the east coast of the US, but Europe shows a very strong use of water in manufacturing, and we can see here that parts of China and Eastern Asia are also using a lot of water for manufacturing. If you decide you want to do your project on something like this, there is an article here that you can access and read more about that study. So industry is the second largest user of water. It's right behind agriculture. And some more facts about water industry: the global demand will exceed viable resources by 40% in 2030 if we continue business as usual. So that is right around the corner. And It is a crisis in much of the world. It's definitely a crisis in the US. If you are not aware of water rights, water usage, and the crisis that farmers are in with accessing fresh water, you should be. It's going to affect us. And I think it's like many things in our society that we often in the United States are very removed from environmental issues unless we care about them and we are concerned about them. And what I mean by that is we live in a very monetary driven economy. We're very, very successful and we rank very high in terms of living standards in the world. And that means that we're separated quite a bit from our resources by money. And if you think about things like how are the dairy farms in the US doing? How are the farmers that grow produce doing? How are the fisheries doing? Well, if you are keen on finances and you really think about where your money is going, you might be aware of that, but you probably don't give a lot of thought to dairy because it's always at the grocery store, except for during COVID when there were now issues with transportation. I can't ever remember not being able to get milk. I just didn't have to think about it. Every once in a while, maybe I had to go to another store, but it's rare that it even runs out. It just seems that it's always there. Things like produce, yes, there's a seasonality to it, but I can't ever remember not being able to get produce in the grocery store in my lifetime. Now, that's my experience in the United States. I have worked and lived in other parts of the world, Mexico and Africa, most notably, where it is an issue. And sometimes you don't have things available. And it opened my eyes to a lot of that. So, and also studying this subject matter, you become aware of it. Let's move on to fact number 3 that the global water demand is for manufacturing is anticipated to increase 400% by 2050. So putting facts 2 and 3 together alone means we cannot continue business as usual. We can't exceed viable water resources. Humans need it to survive. And the pressure will come at some point, and it already exists. Many of the world's wars are driven and caused by water issues, and so it is not anything new. It may be new in your life circumstances, and certainly what I like to think of as our bubble. And my bubble, I think I mentioned before, and I'll talk about my bubble for water. I don't really worry about fresh water, but I have lived in places where I did, and it became crucial and it became a factor. But here in the United States, I conserve water because I live in California, which is a drought area, but it's nothing like life or death. Not in my middle class existence. Moving on to number 4, realizing a circular economy could globally divert up to 340 million tons of waste from landfill each year. And so this definitely impacts our global water supply. Okay, shifting gears again, I want to talk more about the nitrogen and just revisiting this topic and giving you some more detail than we started to look at in the last lecture. Biological nitrogen fixation is where nitrogen is converted into ammonium, and that is a form of nitrogen that a plant can access. Microbes do the job of biological nitrogen fixation, and so they have formed symbiotic relationships with plants. They live in the plant tissue, and they use carbon that is supplied from photosynthesis by the plant for their energy, and in return, they share ammonia to the plant for nitrogen fixation. So nitrogen, as you may recall, is a building block of protein. It's necessary to build tissue. The stems, the leaves, and the roots need nitrogen in order to make those building blocks of their tissues. And this is one of the processes by which plants are able to get usable nitrogen. because when it's in the form of N2, which is two nitrogen molecules together, it is not easily accessible to the plant. It needs to be available as NH4 in order for nitrogen to be utilized in the uptake and build of tissue. So a little bit more about the nitrogen cycle. These nitrogen fixing processes on land combined with others that take place at sea create an annual flux out of the atmosphere of approximately 200 megatons of nitrogen, or 200 million tons of nitrogen per year. And where does nitrogen also come from? In lightning will cause nitrogen and oxygen in the atmosphere to react. This produces nitrous oxides that fall or are washed out of the atmosphere by rain and into the soil. That is a smaller amount of 30 megatons. So this schematic should look familiar to you. Again, it's from chapter 4, and it is summarizing your nitrogen cycle. And I want to apologize. I misspoke in the last lecture. I told you that the reference to a figure was outdated, and I looked it up, and I actually did update that. It refers to your free PDF that I have provided for you. And so while I am giving you the slides to use on your exam, I don't want you to ignore that free PDF. And so not only did I misspeak, but I think I misled you. I really want to make sure that you are accessing the sustainability text that is available through a company called OpenStax. It's also going to be in your Canvas module as a PDF. So that's where this comes from. So we've seen this, be familiar with it. Again, this is something I would ask you to think about deeper and interpret. And while the inputs of nitrogen from the atmosphere are important, the majority of nitrogen comes from ammonification of organic material, which happens in the soil. So organic material is matter that comes from once living organisms, not organic in the grocery store. We've already talked about that. Ammonification, a little bit more detail now, comes from the release of ammonia by decomposers, which are your bacteria and fungi. And they're breaking down the nitrogen compounds in organic materials. And then plants are able to absorb, or a process called assimilate, this ammonia. Nitrogen is lost by denitrification, washing out or leaching, and also it's cycled back when organic material burns into the atmosphere. So denitrification is when bacteria grow under oxygen depleted conditions, and this is favored by wet and waterlogged soils. Nitrates are washed out of the soil as runoff in drainage water, and this is very, very common, especially around agricultural lands. There is a lot of difficulty keeping topsoil on the earth because the natural ecosystem will wash it away or blow it away. And then again, when material burns, we have nitrogen that will be released into our atmosphere. So eutrophication is the process when decay is accelerated by an unusually high supply of nitrogen. It's not always negative. We looked at the example of the dead zone off of Louisiana in the Gulf of Mexico, but we also get natural eutrophication inland, and this is an example of that filling in of a lake, which we have also talked about. So I'm just mentioning it again, and its role in the nitrogen cycle. So you can see that the sediment is increasing over centuries in between our example 1, and then over time, same geographic location, example 2. As the sediment builds up, more plants are growing because in the water, because they have access to sunlight and to soil. And so we get that filling in essentially of this water source, which was once a deeper lake, and now it's moving closer to being swampland. And that's what a swamp is. And so, if you've ever thought about a swamp and how do we get these very large extended areas that are swampy, and there is vegetation, but it's not really open water and it's not really land. And this is the process by which swampland is created. So, excess nitrates in water supplies have been linked to human health problems, and it's important to reduce nitrogen pollution, and the focus needs to be on the efficiency of fertilizer use, doing different kinds of feeding procedures with animals to reduce nitrogen content in their excretions, and better processing of livestock waste and sewage sludge. Um, so at the same time, we have demand for food production from a growing population. There's a greater appetite for meat, and it's driving greater fertilizer use. It's also driving more production of livestock, and that creates more waste and sewage. And so whenever you have a process, any manufacturing process creates waste. So when the amount of nitrate in the soil exceeds what the plants are uptaking, the excess is leaked as drainage and it goes into our streams, rivers, or oceans. It's denitrified by bacteria or lost to the atmosphere. And one of the main gases that is produced by denitrifying bacteria, nitrous oxide, is an important greenhouse gas, and this contributes to global warming. We hear a lot about CO2, but N2O is also a greenhouse gas. Now, a greenhouse gas you may not have ever considered, if you haven't heard this, is water. So, greenhouse gases basically trap heat in our atmosphere, much like a greenhouse traps heat in order to aid growing plants and seedlings. And so, it's not just CO2, it is a complex set of interactions. And nitrogen is important in part of that. So, if we look at where is nitrogen coming from, the N2O, mostly agricultural soil management. Again, I am not against farming. A big fan of farming. I like salads. I like dairy. It is just that the practice of agriculture is problematic with the environment, and so managing these kinds of things is one of the ways we can try to manage our growing population numbers. We also get N2O from power plants, chemical production, manure management, and transportation. Just another way to show you human sources of nitrous oxide. Again, looking at it in 3 dimensions, just driving that point home that agriculture is the primary source of nitrogen. Also want to point out here this blue slice of the pie, light blue is 9% and it's atmospheric deposition. So it is part of a natural process. Biomass burning is also a natural process. And one of the things that I found striking in traveling through parts of Africa were the amount of fires. And I flew between several countries while I was over there, and I traveled extensively through some very wild regions of Zambia, and I saw a lot of fires burning, and they are a very common part of the landscape, and they would be in the United States if we didn't put them out. Okay, so how are humans interacting? We've talked pretty extensively about all of these processes here. Algal blooms we've touched upon, eutrophication we've touched upon. So what I want you to focus on here, again, we did also talk about agriculture and livestock. There is a great deal of urban runoff and residential runoff. And the reason that I want you to look at this and pause and think about it is that these are all areas that we can use our technology in order to affect our contribution to these cycles. And so if there is a way for us to reduce algal blooms that are causing dead zones, that would be a very good thing. If there's a way for us to reduce urban runoff, if there's a way for us to reduce runoff from agricultural fields and livestock farms, as well as residential areas. And there are some really, really great examples of technologies that have been developed in recent years on projects that are addressing this. Okay, when we think about greenhouse gases, we already talked about carbon dioxide, and we just recently talked about nitrous oxide. Methane is also a very popular or very important greenhouse gas. It's not so popular, I guess I should say. Methane, the primary source of methane, according to some scientists, is from cows. And this might sound sort of juvenile. And when I'm teaching a face-to-face class, I will ask my students, how important do you think cow farts are? And I get giggles and smirks, but the methane from our livestock and from domestic animals, because they're so concentrated. And remember, the whole idea of a livestock farm is you are concentrating a lot of animals in a rather unnatural condition. So it is creating an imbalance of methane in our atmosphere. Okay, so I'm going to look briefly at this is a slide presentation from a site called Prezi, and I want to show you how humans interfere and impact the nitrogen cycle. So humans combust fossil fuels and they use fertilizer. Combusting fossil fuels releases nitrogen into the atmosphere. This creates nitrogen-containing compounds. This, in turn, leads to acid rain and other forms of air pollution. Negative outcomes include excess runoff of fertilizer into lakes, streams, and other bodies of water. A major cause of eutrophication is excess fertilizers from agriculture. I should point out here, it is a major cause. There are natural types of eutrophication that don't come from fertilizer. We saw that in the lake example, and it is a natural process. It's not just man. I will say that probably several times, especially when we talk about climate change. The whole idea is that man's activities tend to be driven by the capabilities of technology and not the limits of natural systems. So let me say that again in a different way. Man has the ability to out-engineer what nature can keep up with. We can create bigger and bigger and bigger shovels. And if you picture in your mind the evolution from using simple shovels to create a garden in your backyard to huge tractors that are plowing large fields, we have the technology to do that. The problem is that Earth's ecosystems have a difficult time dealing with the ramifications of that kind of technology. And so there's a lot of examples, and using excess fertilizer in one area concentrates a lot of chemicals that end up in waterways that are not able to handle the load. Humans manage nitrogen by restoring wetlands and governing how people use nitrogen and creating policies for it. So not only focusing on ecosystem restoration, but practices that are contributing to this imbalance are important. There are laws that protect air and water pollution from excess nitrogen. So we've seen this before. Just a reminder of how much of our atmosphere is actually nitrogen. So it is necessary. We do need it in our atmosphere. We do need those inputs. And it isn't just a problem. Again, the problem is imbalance in the cycle. I'm going to leave that there for you. If you want to look at sources, it is available for you to look at on your own.